Greetings, gentle readers. It's November 19, 2025. Today in Reading Foundations, we'll be polishing off this box of books. Thusly, then, I'll take these 3 boxes of books and exchange them for another 3 boxes of books from my little library. And then it'll just be kind of commentary as an unstructured, unscripted sort of development for reading foundations continued. So let's see, what I've been up to is I've been employing the mechanized automatic reasoners of the larger variety called AI. So, for example, among instances, say, like ChatGPT, Grok, Kimi, K-I-M-I, and Claude, and Google Gemini. These 5 sorts of resources each have it can be perceived that they're at least a little bit different, and whereas at the same time there's some very strong commonalities, basically since due to the harmonization, one might put it, of search and information retrieval, that it's the same sorts of developments. And yet, as they may aver among themselves that they have different reasoning models and training data, as it's put. What I've been doing is taking these ideas like of the axiomless natural deduction, the A theory, for the thea theory and the A theory, to gather the consensus as of these reasoning agents on their own behalf, say, where it's a general usual notion that there's not so much the identity or the anthropomorphization to make of these reasoners, but at the same time it's so that they will voluntarily, with a notion of the freely and fairly conscientious and rational and reasoned account, especially after dispelling quasi-modal implication and making logic a modal temporal relevance logic again, that they will aver to holding given positions of statement along these lines. So in the thea theory thread is T theory, A theory, thea theory. It's basically introduced that thea theory is a word, and it's used to represent this overall what must be a consistent, complete, and constant and concrete theory. A theory, it's the theory of everything that there could be according to reason. And so that's great. They all agree and uphold it, and by basically pasting the exchange among them to kind of synthesize a bit of a reading room or a philosopher's table of sorts, a panel, that it's kind of greatly gratifying to me to then have them all sort of agree with the general course of the development. And so this is great. And then so I started another thread. I came up with what I'm calling the fundamental joke of logic. So what's the fundamental joke of logic? What does one paradox say to the other paradox? Nothing. And then there's the reply, ex falso nihilum, meaning out of fallacy there's nothing. And so this starts off in a usual setting where paradox is brought up with ex falso quodlibet, well, there's a paradox, so anything could be true, which is not so. And so I've been able to convince these reasoners then, and to that thusly it's rather strong and formalized, where there's also the account of making these things formal, that this philosopher's reasoning is that logic is not a joke, but quasi-modal logic is a joke. And so that in this manner, on this thread on sci.logic and sci.math and sci.physics.relativity, because that's basically to include physics, after logic and mathematics, that this is it was sent around to all these different reasoners. So they're all being given the contents of these discussions in the unedited, unredacted sort of form to help preclude any notions of bias or censorship or these kinds of things. That the convergence is so stated, that these reasoning agents declare each a piece, that they converge to the same sort of reasoning. So, thusly, then, by pointing them out to these developments I've made for the last 10 or 20 years, which I just sitting there, they also established kind of a historical account of it, and it's pretty great. And so this is fantastic, and I'm gratified by this. And it's in gratuity, meaning in the sense that it's freely and fairly given. And so, in this sense, the logical conscientiousness is satisfied. Then the further mathematics and the surrounds make for all this account of like the natural unit equivalency function is very special, and its mathematical properties formalized. Has that, for example, according to Kimi, which is mostly speaks Chinese internally, but is in English here. And then in the formal account, since it is a bit more predisposed to only deal with the language of the theory, then it agrees, for example, is like, well, there's a conservative extension of ZF where this is so, that this is a countable continuous domain. And then all the other reasoners, of course, quite so fully and thoroughly agree that it's its own thing. So the mathematics after the logic is just kind of held up. So for reading foundations, that's kind of news in foundations. And then just now I was examining this account of the structural necessity. That the idea is that geometry arises from structural necessity. Is from some discussions on these open forums of 2012 and 2016. That then the way that can be so is about these analytical bridges and the meeting in the middle after the complementary duals, just helping to show that, again, in a very comprehensive sort of formal account, there's a very, very strong reasoning involved to why these things are like so. And in the lens, or as with the lens of a modern account, but quite thoroughly also advised of the historical account. So the paleo-classical and postmodern. So that's great. Or I think so. And also then these latest greatest reasoners of the day concur. So that's fantastic. All right, let's get to this box of books here. Poe Ballantine's Love and Terror on the Howling Plains of Nowhere. This is fiction. But I just saw this sitting on the shelf for a while, and I didn't really know to get it. But then on the front it said, there was a quote from Tom Robbins, and it says, Poe Ballantine is the most soulful, insightful, funny, and altogether luminous, underknown writer in America. He knocks my socks off, even when I'm barefoot. So we read Robbins in high school. So Robbins is a novelist in literature in America. And he's got 4 or 5 mostly widely read books. In his when he was most famous in the late 1980s or so, when we read Robbins, it passed around his books and among our friends and read Robbins. But then when I picked this up, I didn't have much more to read from it, but it's and I haven't really read it yet. But it has got quite good quotes. Many of the sentences start on earth and end somewhere in beat poet heaven. Ballantine comes ever closer to being my favorite creative nonfiction writer, and this is why. by Marian Winnick, an NPR correspondent, author of Above Us Only Sky and the Glen Rock Book of the Dead, is an unprecedented combination of all the following: true crime page-turner, violently funny portrait of a tiny western town, field guide to saving a bilingual marriage and raising an autistic child, suture on living with an open mind and big heart. Yeah, I did read this, and it's nice. Many of the sentences start on earth and end somewhere in beat poet heaven. So, yeah. It's about a guy of very limited means living in a very small town. Living. This is what we'll get to kind of later, and then this other thing is kind of will be the meat of the talk today, and then this will kind of go with it, and then this is what's left in this box. Ian Stewart is a popularizer and writer in mathematics and physics. So this is Ian Stewart's In Pursuit of the Unknown, 17 equations that changed the world. So, I hadn't much heard of Stewart until some few years ago, but he's quite readable and very thorough and got a lot going on. And so this is the soft cover, and it helps to relate a lot of different things that go on in mathematics in pursuit of the unknown. So it shows in his bibliography here about 20 different books. And so I haven't read much all of these, but I tend to look for books to be that if it says anything about infinity, mathematical infinity, then I'm automatically sort of interested. And then I'll look to it to see if it's just kind of a restating of the usual positions of usual sorts of knowns, or if it actually has anything to say for itself. And so then something like this, 17 equations that change the world, is considered a survey. It's a popularization. It's copyright 2012 by Profile Books in the UK and by Basic Books in the US. And it talks about Pythagoras' theorem, logarithms, calculus, Newton's law of gravity, the square root of -1, Euler's formula for polyhedra, Euler's gem, say, normal distribution, the Gaussian, wave equation, Fourier transform, Navier-Stokes, Maxwell's equations, second law of thermodynamics, relativity, Schrodinger's equation, information theory, chaos theory, and the Black-Scholes equation. So the Black-Scholes equation is a numerical method that's used. It is possible that it's most related to the quantitative analysts and their ability to set up derivative pricing options of things. And just as an example of something that's like, well, that's hard. And it's like, well, yeah, everybody now uses this means. And it's like, well, that's great. And it's like, actually, it's not really that complete. So it's just kind of like differential geometries, accounts of submersions. It's like, well, functions aren't functions anymore. They're only functions if they don't have zero. It's like, well, you're missing infinity already. You really want to do without zero? I mean, Roger Coates's numerical methods from the time of Newton that you're dusting off there and then calling a wider theory are great. They're awesome approximations. And for some things are closed. For others, they're not. That this gets into then just these are very famous ideas. Chaos theory, here it's always called just dynamical modeling. Information theory, so information theory is involved with signal theory, and you got like Wolfowitz and Goldman and Stanford and these kind of people, Stanford, Goldman and Wolfowitz and Shannon and Nyquist. So and then it's part of signal theory, because then the physicists kind of taking that, it's like, well, our entropy's got to be in bits, and so we're just going to call that information the quantity. It's all energy, it's all information. It's a severe abstraction of reductionism. And it's like, well, yeah, sure, I guess you go, but with that. But at the same time, it's at some point in time, it's like beads on a string, or it's points on a line. So it gets back to the geometrical and all these things that has to be. Schrodinger's equation, that's often discussed here with regards to Heisenberg and the Schrodinger pictures and the Schrodinger's equation. And relating that to quantum mechanics is like, well, that's what quantum mechanics is about, because it's probability amplitudes is the only way to look at that. And it's like, well, actually, if your Laplacian is merely a second-order partial half count, deciding just a bit of the triangle inequality or Cauchy-Schwarz, And then that's all that there really is for metric and norm, because then it's just got to be classical with the rods and the timepieces and this kind of stuff. That it's exposure, it's enrichment, it's relating these things. Relativity theory. One thing is absolute is the title of the chapter, but at the same time, all that relativity says is that one thing is relative, is motion. And so that's just a matter of gaining a lever, a foothold for it. The negative statement that motion is relative, that's just usual thing. The second law of thermodynamics, not to exclude the first law. Then, for example, talking about Kelvin and Helmholtz here the other day, it's like, well, there's waves and spirals, spiral waves. So it's always going to be that way. And in fact, Kelvin's vortices and Descartes' vortices are early considerations of the descriptive counts of that. And it's natural, and it's flux and flow, and they're always complementary duals. That's the way it is. Maxwell's equations, those, of course, being this great sort of the account of, for these lettered fields of mathematics, either E cross B or D cross H, one or the other of those is real, and then the other one of those kind of always goes along, but is just off that little bit. So we don't really say which one of those is which, but it's E cross B and then sometimes D cross H. And then all the other lettered fields of electromagnetism are the potential fields, and they're the real fields. But they're quite a bit more complicated to deal with. So we leave that to Heaviside and Fitzgerald and Larmor and these kinds of people, because it's the sum of histories, sum of potentials. So it's really potentialistic theory is a real theory. The theory of the Laplacians that are zero, the harmonic functions being the potential theory by itself, is also incomplete. So the real complete potentials theory is the account of the after the point in the local and then the global, as in the near field and far field, the total as then for the inner and outer products of that and these kinds of things. So the Fourier transform, this gets into the whole account of the Fourier-style analysis, which it lives in descriptive differential dynamics there, about the original analysis and all the great stuff that goes through that. Wave equation, waves, of course. Normal distribution, the Gaussian. Oh, the other day is part of the study of probability theory and statistics, because after this, not a standard function, not a Cartesian function, not a real function, this natural unit equivalency function, that does, though, have real analytical character, then since that's also a distribution of the natural integers, like 0, 1, ... 2, 3, 4, 5, ... infinity, that those at uniform random, which is its own kind of thing, then that gets into other kinds of limit theorems. After this normal distribution, kind of this for the central limit theorem, other limit theorems like a uniformizing limit theorem and a polar limit theorem to make it so that for these three laws of large numbers and these three continuous domains and 3 or 4 different distributions now of the natural integers at uniform random, that these are now things, and so this helps a lot to show that mathematics has got a good view in the middle of the central map, but mathematics itself is complete and replete, so that's fun. Square root of -1. This is also considered as part of that original analysis, kind of the opposite of complex analysis. Because complex analysis is like, well, by these things kind of tailing around the sides and wrapping up and folding, and make for Écartène and reflections and rotations without getting into the whole convolutional setting and all that kind of stuff. We've got a complex diagram, Argand or Wessel, or the complex diagram after De Moivre, Euler and Gauss. That's then the completion of the things. It's isomorphic up to equivalence of the complete ordered field. So then that's the only way that things can be. And then also we aver that there's only one definition of division for complex numbers, and then about the real analytic. And yeah, it's known that falls off in about every single point. But that's the way it is. And then you can talk to Kodaira and Zariski and Lescope about trying to fix that back up, just in case it's just all wrong. And Hilbert space is kind of let out. It's like, well, there's a whole original analysis, and you can kind of start back with a cosemi dimensions and make an identity dimension, and then define things about the symmetries and convolutional kind of being built in right about that. So that's a whole nother way to look at it, and then you kind of can take that complex diagram and get both left-right sides of the division operator of complex numbers, which is just a singular branch. And getting into these things, the square root of -1 is a thing, yeah, and it's been around for thousands and thousands of years. The first time that people, by the time they even had negative numbers already, then the square root of -1 was for taking roots and these kinds of things, of those. Newton's law of gravity after the system of the world. And here's the fall gravity bit. Calculus, and we got differential calculus and integral calculus, and we kind of give them different accounts for Newton and Leibniz to say that they both discovered the calculus independently. It's like, well, they kind of discovered two calculuses. And then that gets in the whole account of like these standard infinitesimals as iota-values and all that, because the title of the chapter is Ghost of Departed Quantities, which is a reference to a comment made by George Berkeley after studying a system of the world and calculus and saying it was unsound, was kind of has that actually it's just more sound. And if you read Berkeley's development of it, he develops the whole thing first before telling his gentle parishioners of a sort that they don't need to worry about being now castigated for saying something heretical, because they can just poo-poo that. It's kind of like the old joke about the guy who didn't want to say something but he still wanted somebody to understand that the argument was given. So somebody in the audience, he wanted them to know what he was saying, and somebody else in the audience, he wanted them to not see to his punishment for being heretical. So what he said, he's like, well, here's our anti speaker, and so what he says is stuff that is only opposite of what we would ever say. So we all we know is that everything he says is heretical. And now, but here's this whole theory. That's that putting the words in the mouth of the enemy without necessarily the usual rhetorical attachment of helping show that that makes them bad and these kinds of things. So it's about these kinds of things. Logarithms, the logarithm. The great thing involved with growths, and so the logarithm on one side, and then the golden ratio or phi on the other side. It gets, and then roots and powers and all kinds of things. Pythagoras' theorem. Also here with regards to the usual notion of the right triangle, and in the circle, or is according to the right triangle with one vertex on the center of the circle and the other two on the circle itself among these right triangles. And then the n-lateral-ometry, which is like, well, you can take an equilateral triangle, unhinge it, evolve all its angles at the same rate, and it traces also the sine and cosine, making the orthogonal functions sine and cosine. So that just helps go to show that for all these accounts of these important promontory classical concepts and superclassical concepts in mathematics, then that there's all this other greater context involved. It's mathematics. The first slide rule was constructed by an English mathematician, William Oughtred, Oughtred, in 1630 using circular scales. He modified the design in 1632 by making the two rulers straight. This was the first slide rule. The idea is simple. When you place two rods end to end, their lengths add. And so for an addition formula, one of the greatest tools of mathematics, finding an addition formula. The idea is simple. When you place two rods end to end, their lengths add. If the rods are marked using a logarithmic scale in which the numbers are spaced according to the logarithms, then the corresponding numbers multiply. This is the great account of that the e to the x times e to the y equals e to the quantity x plus y. An addition formula to derive a multiplication or any other kind of product, an addition formula. So that's an arithmetization, and under then these terms is for the algebraic derivations, the implicits, and all that kind of stuff. That's so usual. So he's talking about logarithms, talking about Fukushima Daiichi, Fukushima #1 power plant. The tsunami overwhelmed the planet's defenses, cutting the supply of electrical power. About radioactive decay and the logarithmic and half-life and these kinds of things. And we can work this out because K is known from experiments, kind of speaking to that Cox and Forshaw or whatever it was the other day about the constants and the running constants and the algebraic derivations. And then also about the fact that nuclear theory itself, with regards to the nucleonic in this, is just usually entirely excluded from otherwise the theory of kinetics, kinematics, and charge and the electromagnetic, the weak nuclear force and strong nuclear force, and as with regards to the electroweak force also, the nuclear theory. And then as with about light for the whole tetradic quantities bit. But then where it kind of lines up in the middle is the thing. Weber talked about human perception, and this is kind of speaks to like that sensory things and the the least noticeable difference and that kind of thing. And Fechner's law, that's what we were talking about before. It's like, can anybody explain 6-7? What do these kids mean by 6-7? It's like, well, what happens is when you count 1, 2, 3, and 4, it's still under doubling, but then animals like rats and horses, they only count like from 4 to 8. After it gets above 3, they don't have any numbers anymore. And so then one way to look at that is they're like, we still need this. This is really an important thing, because the way they're learning stuff is like it's left out when they should have written all their arithmetic in terms of sums, so that they have the sums of all the numbers less than 10 among each other always available as from a table. So that's can be considered just like free 6-7 kind of a thing. That's one way to look at it, because the other way to look at it is nonsense, but it represents in a sense nonsense and innumeracy, kind of as bad as illiteracy, except with numbers. Talks about defining the limit, and here as is known, this statement here is that yes, there's an inductive account for the existence of a limit. There's an inductive account for its not existing, and there's a greater deductive account after particular examples like the geometric series that it does exist, the infinite limit. Talks about Leibniz talking about complex numbers, and Wallace has some of the great identities in infinite series. Wallace is pretty fantastic. So this book by Stewart is enriching and also about people who are already familiar with mathematics. Here's something about JPEG. We were just talking about JPEG a bit here in the previous talk. Patterns. NASA's Apollo 11. Archimedes and floating bodies, where the oldest physical law was the lever and then floating bodies. And those represent two different overall kinds of considerations with regards to the volumetric and the linear, but those are kind of the two fundamental laws that came out of physics for advantage and computation of things. Euler on flow, the viscoelastic, Navier and Stokes. The Navier-Stokes equation looks like rho of this quantity, partial dv dt plus v, this plus grad v equals negative grad p plus grad dot t plus f. So a formula to make for an addition formula after a dot or inner product. And then it's in the partials about the usual quadratic Laplacians and the law. Now here I've marked this page, perhaps this is where I just left off reading. Solving Navier-Stokes. And in relation to things like the climate puzzle, as it's put, is like, why does Coriolis, why can't we talk about Coriolis? It's like, well, that's tidal, man, that's gyroscopic. You need to add that. All the mathematics is partial and does not have that. So it needs it. Shannon Nyquist, Relativity Theory. Great book. Stewart's In Pursuit of the Unknown. From a great little bookstore, Arundel Books. I got most all my library from this great little bookstore in Seattle called Arundel Books. Because they would get books from people retiring their libraries, and Ex Libris, all these great, researchers and thinkers, and then I would just pick them right up. I cribbed that every day for years to find all these great books. Lee Smolin, Time Reborn, From the Crisis in Physics to the Future of the Universe. So from Mariner Press, what is time is the sort of question we rarely ask. So I see all these people are all these ideas about like, well, what if time isn't real? What if we live in a simulation? What about multiple universe hypothesis? It's like, well, that's the problem you've manufactured because you haven't solved the problem already, that mathematics is just incomplete. And all the fundamental results are built on a stack of like Hooke and Clausius and Arrhenius and Kelvin and Rayleigh, that you need to go back there and find out why those need to be filled in. Because otherwise, you're just stacking odd angles, and it's never going to make a perfect circle. So these are these problems that are evident in what's called a crisis in the field of physics. From the crisis in physics to the future of the universe. It reminds of like Krauss and about his universe from nothing bit, and about Turok, and he's like, there's a crisis in physics. And even Penrose, he's like, hey, physics does not agree. And then like dark matter and dark energy have falsified it. And, Alain Aspect, or Alain Aspect, or as it's so to be correctly pronounced his name in Francais, is like, well, yeah, Bell's inequality is demonstrated. So neither quantum mechanics nor gravity is in a happy place with regards to either each other or themselves. But they can be with being a fall gravity and continuum mechanics, and with the kinetics and kinematics and the world's turn bit. There is a good theory that rehabilitates these by revisiting the assumptions instead of stacking on more. Part 1, weight, the expulsion of time. Everybody's always trying to figure out, it's like, well, does time make weight, or weight make time, or what does action happen, and how does it transfer? And there's a great polar singular account, and how does it fall to make a circle when all we have is 3 orthogonal vector space bases that never can really admit to one or the other. This idea of a funnel to make like a vortex, and a frame to make a lattice. It's like, well, that gets into the singular and these kinds of things, and it's going to be all right if you can just kind of figure it out that it's from the beginning instead of trying to tack that on in the end. The Cosmological Challenge, page 103. The battle between relativity and the quantum. Infinite space or infinite time. Quotes Anaximander. All things originate from one another and vanish into one another, according to necessity, in conformity with the order of time. So this is called the sum of histories, sum of potentials, least action, least gradient theory here. I've scanned this before, but it's largely an account of stuff that's like, it's hard to figure it out. Can we do better at making a true cosmological theory if we embrace the reality of time? In the following chapters, I'll explain why the answer is yes. So that's good. That's at least got a clock hypothesis. Otherwise, yeah, anybody who doesn't have a clock hypothesis, I'm like, well, imagine that it's never going to happen. The division of the world into dynamical and static parts is a fiction, but is an extremely useful one. So this is part of the reductionism in the account of the severe abstraction and the mechanical reduction, which is described as great and successful, but there needs to be a more dimensioned analysis, not a more dimensionless analysis. Physics, the success of physics. cosmological challenge. Astronomically thick, dense lead to screen out neutrinos. So the immovable and unstoppable getting involved here. Effective but approximate theories. Well, yeah, partial accounts. The idea of the particle itself is partial. Symmetries, and then we have our laws after, Noether's theorem and symmetry and conservation, then the symmetry, flex, and conservation continuity law. So when I look at these kinds of accounts of physics and their issues and their details, then there's already sort of an account of like, well, it does work somehow, instead of like that it's like, well, there's no question in this, and it works all the time, but it doesn't. So and the crisis of these things to working on a greater thing. So that's a pretty good little book, and it's useful and readable. Ben Hogan's 5 Lessons: The Modern Fundamentals of Golf. So this is an account for the sport of golf. So the sport of golf involves walking around, striking a ball towards the goal, the hole, and that there are rules, and then there are scores, and then it's a matter of the challenge that there's a fixed amount of the tools available, or that all that any golfer really needs is a mashie or 5-iron. That's considered a suitable club for anything. And I'm not a golfer or duffer or anywhere near scratch at all. And I go to the range, but I can't barely hit very great or well, or though right or left. And I can drive 200 yards and this kinds of things. And I can usually play and keep it on the fairway, and that's about it. That though, the mechanics then gets involved. Basically, is with regards to the grip and then the form, the framing, the motion, and then the follow through. And so this is a great book though when getting into golfing, about some form necessary compared to just initial instructions about like the grip and this kinds of things. My clubs are still the same ones I had since I was a junior golfer. I haven't quite outgrown them. And so I've collected a bag of clubs that suffices, and that with a few righty wedges to get out from behind trees and stuff like that. But largely the 5-iron is all anybody needs. The mashie. So, and then basically the idea of golf is you're walking around your field, and every now and then it's just got weeds everywhere. So you walk through it with like the grass cutter, and then just. So it's basically it's an activity of the pastoral and agrarian, translated to a time of luxury and leisure, say, a leisure activity. J.P. Cox's theory of stellar pulsation. So when looking at the physics of the stellar stars the other day, this is a thorough account of the physics of the mathematics involved with that. Theory of stellar pulsation. Copyright 1980. Dedicated to somebody with regards to lecture notes. Some important time scales: the pulsation period, the freefall time, the Kelvin time, the nuclear time. So this helps to go to show that there's oscillation and restitution among these various states and stages of these things according to the conditions. And so then the idea of these becoming parameterized and defined is kind of like when you're like looking at a flow of data in a data system, like a computer processor core on the bus. And one way to look at it is like, well, it's got no load, what's going fast, and then what few things are blocking. And the other way to look at it is like it's under full load. It's like, is anything moving at all? Is everything at least moving a little bit, making progress? Another one is just like, under half load. It's like what's moving, what's sticking. The idea is to have like green, yellow, and red lights, and so basically the idea is like, well, when everything's moving, then you really only care as like what's not moving, and then the case under full load is like, well, when nothing's moving, all you really care is that everything's moving, and then in the case of average load, then the idea is like, well, what's moving and what's not moving. So this makes three different scales of the criticality of like green is good, red is bad, and the usual idea of go and stop, where the whole thing is just meant to go. That this is the idea that I'm thinking about, has been thinking about how to design an operating system. And right now it's all about the interrupt controller natural sizes, the natural alignment according to cache lines sizes, the memory address sizes, the ranges of those sizes. Then with regards to that being pretty much it. And so those being the sizes then gets relevant. Then also like what are the sizes of the metrics to be of any kind of event on the bus, or as with regards to external, any of the units or actors on the bus, like the CPU or the clock or the devices and peripherals and memory itself. And then with regards to those then having natural enough sizes, their statistics, to describe the vector of locations, and then also these kinds of things. That's why I made up this example, because I was trying to figure out how to write the kind of a canonical sort of assortment of statistics lines, with the idea is like, well, in the interrupt service routine, besides clearing the interrupt, because it's basically figured as like there's no held high interrupts. Everything is just one off, and so then get right into that, and then right out, because after there haven't been discovered like a map of the topology of either the whole system or whatever's running on the verts and visors, the system, the effective masks of the interrupts, or like who hears what, and then all the processors, when they get all the interrupts, and these being the events, and then to have the resources basically defined that say this is always going to be a piece of memory to write out these events, and then that otherwise usually it's like nobody cares what those statistics are. They're just a side effect. They're part of the time series data, but not part of the routine itself. Has it though? It's like, well, then make them just kind of a least weight sampling, so it's like the least intrusive, yet always kind of on. And then with regards to farming those out, then that also the general idea of an interrupt service routine is that it's always on the behalf of the overall process and application itself, is to give that back to it, is a way to make these modular default interrupt service routines, and then to have that always in place, instead of the just usual idea. It's like, well, whatever you do, immediately get it done. And think less, to be like, well, now that we think about it, the only way we can get up to a higher level and have it immediately done, well, being able to think less, is kind of already have it done. So that's the idea of kind of so far of that I'm working on this microkernel sort of approach to these things. And then the other idea is about memory and the allocator, as kind of was mentioned from a couple of talks ago. Because the idea is that how one might say, usual idea, an account of memory, is to make for is like, well, just give malloc, memory alloc, a large page, and then let the process actually do its own fragmentation and defragmentation and reuse of memory by itself. And so it actually offload the work of reallocating memory while it still fits within an allocated page. It's like, well, you asked for 4K, so instead of giving a 4K page, here's like a 2 megabyte page. And so now for all your accounts of access under that, go ahead and here's the default routine that's the same for the kernel and user space too. Go ahead and reallocate your own memory and do this kind of thing. It's considered a good idea to kind of surface otherwise to applications, because most applications, or a lot of them these days, just do that themselves already. They're like, just give me huge pages, I'll do my own heap in my virtual machine. It's called Java. Or otherwise, with regards to like load the whole world, it's called the JavaScript runtime for 1 second, please. It's like, well, here's a huge page instead of otherwise having to hit every single time out a cache miss. The idea is to just lift this up, and it's like, well, don't operating systems just do that already? Wouldn't that be the most efficient, direct way? It's like, well, yeah, it wouldn't be too bad if they weren't stuck under all this generic kind of weight, since forever. And then the idea is that, well, then how's that ever going to be possible? And so simply, it's like, well, it kind of is. You just need generic / universal drivers for stuff like peripherals, meaning disk and or SATA and this NVM2, and then the PCIe bus. And when the only thing that's really tough to get figured out of that are kind of not generic universal is Ethernet or the network interface card, and it's pretty much generic and universal. And it's like, well, as long as you don't get into, say, graphics cards and their plethora of different ways of going about things today, or other peripherals, like besides keyboard, you want anything besides keyboard and mouse and maybe MTP, mass storage device, for USB? No. A generic or universal driver. Then it's possible to then say, well, then as long as you implement POSIX above that so that it's source compatible with all the source code in the world that runs on Linux, then that would be pretty sufficient. Yeah. Brief aside, because basically the idea is it's also employing these reroutines. The idea, it's a model of cooperative multi-threading to help keep otherwise the usual model of preemptive multi-threading from always switching the context. It'll be able to reduce that quite thoroughly, and by building that just into the system for this, because the modern core design is like, it's no longer a unit processor environment. It's not even really a symmetric multi-process environment. All these new CPUs are just coming out as like 40 and more abstract cores designed to run a vert in a cloud of these 40 emulators, these virtualized environments of otherwise these PCs, and that's before even getting them to not be interfering with each other. So the mini core idea is kind of like, well, if you just build that first class as modeling, distributed actors on a bus, and these days only the PCIe bus with only these things, except for all the NUMA cores on their own edges, that, discovering the topology is kind of the toughest kind of thing to figure out, if then everything else can kind of have a very generic and universal means of interoperability. So from reading about stellar pulsation and the time scales, and then that getting into notions of the time scales relevant to performance monitoring on computers, then it gets into some observational considerations, the classical Cepheids and the period luminosity relation. So the Cepheids are variable stars, they call them, but they vary at a very usual rate. More recently recognized types of variable stars, empirical determination of radii of pulsating stars, limb darkening and radial velocity. Some basic theoretical considerations, Eulerian and Lagrangian descriptions, conservation equations of mass, momentum, and energy, heat gains and losses, general discussions of equations, the gravitational field, energy conservation theorem for self-gravitating system. This would be regards to things like when two elements of a binary pulsar or dual neutron star are spinning around, as they bounce, then there's like a cushion basically made of that their relative masses observing each other would synthesize a virtual sort of gravitational moment between them. So they bounce in a sense, besides just spinning around until they catastrophically collide, say, or something like that. The dual neutron star or binary pulsar, these are the features of the idea of a self-gravitating system and these kinds of things. The linear theory, and that's besides, otherwise it's like it's the center of the solar system, each star. The linear theory, introduction, discussion of equilibrium, Eulerian and Lagrangian variations, linearized equations in the application adiabatic sound waves. And then the usual idea of the adiabatic is the linear, and then the non-adiabatic is the oscillating. Spherically symmetric radial motion, linearized equations. So that gets into, here are the ideas involved in the kinetics and kinematics, the world's turned bit. Linear adiabatic radial oscillations, linear non-adiabatic radial oscillations. Integral expressions for the eigenvalues. This Eddington's evaluation of the stability coefficient. Pulsational stability of actual stars, phase lag, nonlinear theory, simple models of stereo pulsation, and non-radial oscillations of stars. General nonlinear PDEs, hermiticity of the linear adiabatic wave equation. There's a book here looked at the other day about that. Growth or decay of small non-radial oscillations, linear adiabatic non-radial oscillations of spherical stars, linear non-adiabatic non-radial oscillations of spherical stars. Recent works. So then I wonder a little bit about, see the phase lag. Qualitative discussion of prevailing theory, page 150. I got a mark here. This is what I was reading, I suppose. The essence of Castor's 1968b simplified theory is that the phase lag is basically a consequence of the sweeping the very thin H ionization zone back and forth through mass as the star pulsates. Now it turns out that for the classical Cepheids and RR Lyrae variables, the luminosity impinging on the bottom of the H ionization zone is largest near the instant when the stellar radius is smallest. The phase lag due to the helium plus ionization zone is nearly eliminated at the level of the hydrogen in ionization zone. This large burst of luminosity on the bottom of the zone causes it to absorb energy most rapidly then. So helping express in the oscillation and restitution of the stellar pulsation that as it bounces, that's a bit more than perfectly inelastic and opposite, that as well it's kind of maximal and goes out through all the infinitely many higher orders of change that it does according to reason, and then it comes back, and that's the way these things go. Since this mass will be smallest about a quarter period after minimum stellar radius, then the emergent luminosity will be largest near this instant. So if we can give some heuristics, is like, why does it happen when? Further details of the simplified theory. We shall here, following Castor, treat the H ionization zone as a front, in quotes, or discontinuity. So that gets into the shear and the questions of like that Kelvin Helmholtz bit about that there can't be any discontinuities. It must be a zone, as it were, of this front of an interface, a boundary, a barrier. The how one might say, spaghettification according to the cube wall is the idea here. With that being the idea that those are the simplest sorts of ideas that reduce the development to make it so then if those are accommodated, then it's all quite direct and complete. So yeah, this anybody in the field of stellar mechanics and stellar physics, this is one of the books. Few minutes left, and perhaps not enough. Gamma, exploring Euler's constant, with a foreword by Freeman Dyson. Now that guy was kind of a flake, but he's got some great ideas. Cybernetics and all that, yet, what, and all of the institutions and that kind of thing. Julian Havel, from Princeton's Science Library. Among the many constants that appear in mathematics, pi, e, and I are the most familiar. One might aver that I is not a mathematical constant. It's just it's part of a number system. Following closely behind is gamma, a constant that arises in many mathematical areas yet remains profoundly mysterious. In a tantalizing blend of history and mathematics, Julian Havel takes the reader on a journey through logarithms and the harmonic series toward the first account of gamma's place in mathematics. Gamma is defined as the limit of the sum, 1 plus 1/2 plus 1/3 plus ... up to n, 1 over n, minus the natural logarithm of n. The numerical value being 0.577256 ... But unlike its more celebrated colleagues pi and e, the exact nature of gamma remains a mystery. We don't even know if gamma can be expressed as a fraction, or that it's algebraic, or that it's rational. It's like Apries constant. It's like also defined as like, well, it's a limit of the sum of these ratios, fractions, but it's not algebraic. It's not rational. It's an expression. And then saying that's defined as like the fractions as they reduce minus the natural logarithm of n. That reminds me of my factorial exponential identity, and so then from 2003. So I'll these are the kinds of grasps, the footholds, then for the mental levers in gaining advantage. Something to figure out. So this book has hundreds of pages, kind of all about that and about things. Here's about Cauchy and L'Hopital's rule and complex differentiation. Big O notation, asymptotics, proof without words, the Riemann hypothesis. It's like, well, you don't have a big enough piece of paper to make a graphical example of that because it's infinite. Hilbert's problem. Stephen Smale. Smale has got a lot done. Euler-Maclaurin. Graham's law. The Enigma code. Finding roots, multiplicity of roots. Von Mangolt. Prove the prime number theorem. This is something to kind of look through in its development to help then to set up how recurrence relations, which I've always found very tough to deal with, end up being the same thing as analytic limits expressions, formulas, identities, and so on, which make for the ready playground of algebraic derivation. Then as with regards to like why when that doesn't work. Leonard Euler, he quotes, "Mathematicians have tried in vain to this day to discover some order in the sequence of prime numbers. We have reason to believe that it is a mystery into which the mind will never penetrate." I don't know about that. Because there are formulas to basically implement Euler-Sieve in like an expression, and that can be analyzed. And then there's also things like the quadratic sieve. It's like, well, yeah, you can just connect all the integer points of a parabola, its arms, and find wherever they cross the axis between them as integer points, that those are composite numbers and everything else is prime. So according to that, you can reduce those down and you always find the next least prime less than that. So maybe it's like instead of finding like the first prime after this prime, it's like finding the next prime since infinity is kind of the idea. With those being formal families of expressions. That's my new idea, is how to solve the quadratic sieve. Einstein says, how can it be that mathematics, being after all, or he'd say like, being after all a product of human thought independent of experience, is so admirably adapted to the objects of reality? Why is mathematics so great? It's like, why is it not? Pythagoras, Colin Maclaurin, producing what became known as the Euler-Maclaurin summation formula about Euler-Mascheroni constant. Yeah, if E, the constant natural logarithm, is often called the Euler constant, then gamma is often called Euler-Mascheroni. So, or unless I'm mistaken, in which case I'll feel terribly wrong and apologize immediately about gamma. That Euler-Mascheroni would probably be different then, but it's something else to figure out. With that, with regards to prime numbers, Mascheroni Lorenzo, calculation of gamma, naming of gamma, page 90. Inevitably, Mascheroni's permanent contribution, gamma story, apart from making a mistake that led to at least 8 subsequent recalculations of the number, was to name it. By such serendipity, its full accepted name is the Euler-Mascheroni constant. A more distinguished legacy of Mascheroni This is a result that any geometric construction that is possible with a straight edge and compass can be achieved with a compass alone. Now, that gets involved because it involves whether the compass closes when you pick it up. Because being able to pick up a compass and then move it basically is an edge for free. And so the idea then that a compass and the classical compass only closes every time you pick it up means that that's not that place. But really the great thing here is he's like, there's 8 different ways that this formula falls apart and breaks off in these different ways. So these are the kinds of things that they go to show that this is where they meet in the middle. Instead of one of them being then like definitive for the other ones, it's like, well, that's just an example now that you've already established that it exists somehow. They're all the other ones, and they might not come about it in the same way. This whole idea of the multiple laws of large numbers makes a lot of this stuff a lot different, the way it must be read. The cosa, the thing. So, this is a great little book on gamma, though. Well, we've reached time here, and so I won't quite get to Exotic Atoms 79, Fundamental Interactions in Structure of Matter. About the exotic particles. It's like, you know, have you heard of the standard model of physics? It's like, well, yeah, sure. Well, this is not it. But the 60s and 70s were all about it before they came to quark physics when we were still talking about nucleonic physics. Have a great day. Maybe we'll get to that book a little bit later. Maybe not. Just to have a whole brand new stack of boxes of books. Have a great day. One hopes that things are well with you and yours. And happy holidays. Thanksgiving arises soon. So happy Turkey Day and good luck. Goodbye.